Okay, I want to pick up where we left off at the end of class so that you have what you need to do the homework. So we talked about this volume function, volume of a sphere. Plug in x as the radius, it spits out the volume of the sphere. Now every time you see a quantity function now, we want to think of it as an accumulation function. So how can we think of this Vx as an accumulation function? Well, so Vx is so how can we think of Vx as an accumulation function? It outputs the accumulated volume as the radius increases from 0 to x. Okay? So that's how we can think of this as an accumulation function. We think of it as the radius increases from 0 to x, it will give us the total accumulated volume over that increase. Okay? Similarly here we have our Rx function. Okay? And so Rx, what is this now? Remember we said this was the volume at the left side of an interval with delta x, and this is the volume at the right side of that interval for given x. Okay, so we have the change in volume over the change in x, or the change in y over the change in x. And we said this is the average rate of change of the accumulated volume at a given radius for a given change in x. So Rx is the average rate of change of the accumulation of volume. So it's how fast this accumulation is changing, okay, as an average rate over the interval of width delta x at a radius of x. So it's the average rate of change of the accumulation of volume over an interval delta x at a radius of x. Okay, so it's how fast the volume is accumulating, okay, as an average rate over an interval, delta x, for a given radius x. Okay, so I want to show you how Graphing Calculator can help us do some algebra. It actually does the symbolic algebra for us. This is a really nice feature of the software. So first of all, we have to know what this expression is. Okay, so we have to know what that means. If the v of x is 4/3 pi x cubed, it's telling us that no matter what we input, we're going to cube it and then multiply it by 4/3 pi. Okay, so what is our input here? Our input is this whole expression x plus delta x. So if that's the input into the v function, this rule tells us what to do with the input. Our input is x plus delta x. And this rule tells us to cube the input and then multiply it by 4/3. Okay, so this first expression here, v of x plus delta x, is we're going to take that input, we're going to cube it, and then we're going to multiply it by 4/3 pi. So that's v of x plus delta x. Taking that input, cubing it, and multiplying it by 4/3 pi. Okay, and so continuing here with the average rate of change function, we're going to subtract v of x. Well, v of x is just our original rule here, 4/3 pi x cubed. Okay, and then we see that whole thing is over delta x. Okay, so there's some really nice features here that I want to show you. The first is, you see that there's a 4/3 in both of these on the top. So we're just working on the top for now. So if I highlight the 4/3, you see a little hand pops up. I can grab, click on the 4/3 and drag it out, and it actually will factor out the 4/3 out of both those terms. Okay, show you it again. So you can grab the 4/3 and just slide it to the left, and it will factor it out of both those terms. And now what's left in parentheses is just what we had before without the 4/3 on each term. I could do that with the pi as well. I can highlight it here. There we go. So I can pull it out like that, and it just pulls it out of both terms. And you can move it inside or outside the parentheses. It does the work for you. Okay. So I'm going to take the 4/3 out, and I'm going to leave the pi inside. So the next thing we want to do is we want to expand this all out. Okay. So what I can do is I can just highlight this part of it and expand that right there. So I can go to Math menu, click on Expand, okay, and it will expand that whole thing. So I'm gonna go back, and I'm gonna copy this and paste it so we can see where we've come from. So again, I'm going to grab onto the pi times x plus delta x quantity cubed. I'm going to expand, and now it just multiplied out, it cubed that binomial x plus delta x. Okay, so now we notice that we have a plus pi x cubed here and a minus pi x cubed here, and those would subtract to 0. Well, let's let Graphing Calculator do that for us. So I'm just going to do that. I'm going to copy and paste again. And so we can see the process here. So I'm going to highlight that whole thing, and now I'm going to go to Math, and it's not expand this time, but simplify. So when I simplify, watch what happens. It found that those two terms simplified out to 0. Okay, now I want you to notice that what's left in all three terms is at least one delta x. So I can highlight just like we did before with the 4/3. So let's copy and paste. So I'm going to copy, start a new line, paste. So just like before, since there's a delta x in all three, I'm going to factor it out by grabbing on that delta x and just sliding it outside the parentheses. Okay? And so in the next, I'm going to copy, paste. So now we notice by doing that, we see that we have delta x here in the numerator and the denominator. So I can take this whole thing and do simplify, Math, simplify, and you see those delta x became 1, and so they don't appear anymore. Okay, so now what I want to do is I'm going to pull 3 out as well. And when I pull 3 out, I can even pull 3 out of one that doesn't have 3, and it'll change that to the 1/3. Okay, and so then notice that the 3/3, we can simplify that. Gone. All right, let's copy and paste one more time. Last thing I want to do is I want to move the 4 back in. So I'm going to grab that 4 and move it back in. So now I have this expression that's equivalent to our initial average rate of change function expression that we started with here. Okay, these two are equivalent. Okay, what we have then is this expression now is equal to our original expression, but the difference is that we no longer have this delta x in the denominator, and now we can apply the idea that we want to let delta x get very, very, very small, and when delta x gets very, very, very small, this is essentially 0, so is this. This piece is essentially 0 as well. And that leaves, for our rate of change function, this term right here, 4 pi x squared. So let's graph that. Graph that red. Okay, so what have I just graphed? I've graphed the exact rate of change function for the accumulation of volume of a sphere. So let's compare that to our average rate of change function, and we'll start with a delta x of 0.1. So I can graph the rate function and right now delta x is 0.1. Let's do that in blue. And so we see that that average rate of change function it's approximating the exact rate of change function, but it's not exact because it's not coinciding with it. So the blue one is the Rx, is our average rate of change function for an interval width of delta x. Okay, and the red one is our true actual rate of change function of the accumulation of volume. So we want to find out how in this particular case, how small do we have to make delta x so for them to be virtually indistinguishable. So on this scale to Ri, they're clearly not the same. So maybe let's try, we'll start by doing half as wide as before, so 0.05. And we see they're still distinguishable. We still see the red graph from the blue graph. But certainly the blue graph is now closer to what the red graph was. So let's try 0.01. Okay, so now we're getting in the ballpark of almost coinciding, but you can still see, especially if you zoom in, you can still see this difference. So let's try 0.005. And we're almost there. Here out, you can still see that there's a little bit of a distinction between the red and the blue graph. So maybe 0.001. So now we're looking at a delta x that's getting us a very, very close approximation to the actual rate of change function. Okay, using the average rate function. So if we want to be safe, we can just go to 0.0001, and this is a very, very small delta x now, and just to our eye and to the resolution of the graphing software here, even if I zoom in a couple times, the graphs are pretty much right on top of each other. Okay, so if I were to come here and get an ordered pair on the graph, let's get something, say x is 0.2. Up here we see that x is 0.2 and y is about 0.503. So let's write that out here. So this is our rate of change graph, and so we have the ordered pair 0.2 and 0.503. So what does this ordered pair mean? What is it signifying? Well, we know that this is our x value, and it's radius. So we're saying for a radius sphere of 0.2 and whatever unit that is. So let's say inches. Okay, so the sphere has a radius of 0.2 inches. This is not the volume of the sphere, but the rate of change of the accumulation of volume. Oh, she likes that. So this is the rate of change of the accumulation of volume. And so what would the units be of that? How fast the volume is changing? Okay, so that's going to be in inches cubed per inch of change in radius. Okay, so this rate of change is saying that the volume will change half a cubic inch per change of 1 inch of radius. when the radius is 0.2. So that's an interpretation of this point on the graph. When the radius is 0.2, the volume is changing 0.5 inches cubed per inch of radius change. Okay, so I've posted the homework and hope that helps you to work it successfully. We'll see you on Monday.